All right, getting started with our weight and balance section. We'll finish off some weight and balance topics here. Then we'll get into our groups for our last group activity today. So weight and balance, of course, is very important as it affects the performance of the aircraft. So you should have a good idea how things are affected when you move the center of gravity around, but we're going to just kind of go over and review some of those concepts. Discussion page for you if you got some questions to throw in. Let's start off with standard and basic empty weights. When we look at a fleet of aircraft, generically speaking, that fleet has a certain weight to it. It's not a number that we generally use for performance calculations. It's more of just a general number. Okay, a Cirrus aircraft, the fleet weighs somewhere around 2,300 pounds. Some could be more, some could be less. So when we look at specific specific aircraft, the registration number, that particular aircraft has certain optional equipment installed in it. And so we just take the standard weight of the aircraft plus any optional equipment, and we come up with the basic empty weight. And that is our number that we're using for our calculations in the weight and balance. So if you go out to the airplane and you open up the approved aircraft flight manual, look at the weight and balance numbers in there, that weight you are seeing is the basic empty weight of the aircraft. Now here at Western, we've done a very nice job of giving you some convenience by putting those numbers into ETA. But always remember that the official numbers for the weight and balance are in the approved flight manual. Some measurement terms, most of these you probably remember from your private ground school. And datum is our measuring point along the fuselage. So our seats that are at a certain datum point, certain number of inches back from that datum. Baggage area, the fuel tanks, anything that we can put weight in. The term arm is that measured distance from the datum point. Now, different manufacturers will state that their datum point begins at a certain spot on their airframe or an imaginary point ahead of the aircraft. And for the Cirrus, that is what they've chosen to do, is an imaginary point ahead. Cessna, on their single engine airplanes, they like to use the firewall as their datum point. But different manufacturers have different rules for that. With transport category aircraft, a new term, fuselage station. It means the same thing as arm. It's distance measured from the datum point. Okay. And this can be abbreviated with FS. Okay. Or they might just simply use the word station in a drawing, in a question, in a graph. So we're talking same thing as arm, so don't be put off by that. Center of gravity, obviously, is that imaginary balance point. And that is measured from the datum. I'm going to try a top hat question here. We're going to be choosing all that apply. Multiple select question, arm is the same as. No one went for choice C. Very good. That was a term I made up. I made up B as well. So, fuselage station, station FS. You got it. All right. Again, documents. Weight and balance documents are always going to be found in the approved airplane flight manual as the document in the aircraft with the serial number and registration number of the aircraft. Of course, that Western is the orange binder in there. A copy of that book is known as the Pilot Operating Handbook, POH, or Information Manual. Again, those are just copies of a generic aircraft, not a specific one. So remember, the AFM is required document in your aircraft. All right, let's move into review of stability of the aircraft. You have this in your private ground school. You probably didn't touch much on it in instrument ground school. When we look at stability, and this was definitely demonstrated to you at some point, given a trimmed aircraft, your instructor showed how the aircraft can return to its original flight path if disturbed from it. And your instructor probably had a trimmed airplane, pulled back on the yoke and let go, and you saw it oscillate up and down with the nose attitude until it leveled out again. That is stability. Now, we have two flavors of stability. First of all, static. And that is always going to be our initial tendency. What's the first thing that the airplane does when disturbed from the flight path? If it wants to return back to where it was, that's positive. If it doesn't do anything, that's neutral. Or if it continues to go away from it, that would be negative. Okay. The other critter here is called dynamic stability. And this is going to be over time, we can see what happens. And this is where the oscillations would occur. Positive meaning we are getting back to our point from which we were disturbed. Neutral means we're just going up and down, not making any steeper or shallower oscillations. And negative is getting steeper and steeper in the oscillations. So when we think about stability, and the loading of the aircraft does affect stability, an airplane that is slow to return to equilibrium is less stable. So the longer it takes to get back to its trimmed condition, that would mean it's less stable. I'm going to think about this one before I start the timer on this one. It's called longitudinal stability. You got to think about the different axes of the aircraft. So let's think about, first of all, a longitudinal axis, runs from nose to tail. So you've got that picture. Okay. An airplane rolls about that longitudinal axis. Okay. Now think about the other axis, the lateral axis, wingtip to wingtip. You're picturing that. An airplane pitches about that. So just trying to draw a little comparison in your mind here. When we think about longitudinal stability, we are literally thinking about the longitudinal axis not remaining in its plane. Longitudinal stability is a pitch stability of the aircraft. So that'd be another word to put in there. So when we think about longitudinal stability, we're thinking about pitch stability and the ability of the nose to remain in one plane. So that now that you've got a good thought about the question here, see if you can answer the question. All right, here we go. All right, most of you got that one right. Most of you were listening very well. I even gave you the answer before I started the timer there. We are talking about pitch stability. Longitudinal axis is what we're talking about. Longitudinal axis stays in its plane. That means the nose stays in one spot. You're stable. If the nose is pitching up and down, it's oscillating, you do not have longitudinal stability. Okay, controllability, probably a new term for you, not normally covered in your private ground school. This is the capability of the aircraft to respond to control inputs from the pilot. So when I think about controllability, I'm actually thinking about the control yoke, the control stick, and how far I need to move it to get the airplane to respond. So using the reference here of I have to move the yoke a ½ inch forward to get the aircraft to react versus I need to move the yoke 2 inches forward to get the aircraft to react. That's controllability. Hopefully your instructor demonstrated this to you a long time ago in your private training. I know with my beginning students, we would fly the aircraft, just put it into a dive at about 120 knots, sample the control inputs, see it's very responsive, and then I would pitch the aircraft and slow down to about 80 knots and sample the controls. And notice, wow, I got to move controls farther now to get a response out of the aircraft. So this is controllability. If you need large amounts of control deflection, I got to move the yoke, which in turn moves the control surface. You need a large input, then you're less controllable. And one more new term is maneuverability. The ability to easily change the aircraft's movement about each axis. It really comes down to how hard is it to move the controls? So muscle power. Think about your muscle power and moving a control surface. Is it hard to move? You got to put a lot of effort into it, or is it very easy to move? Most of you should be able to fly the Super Decathlon later, and you're going to go from flying Cirrus or Seminole, and when you, of course, fly those airplanes, you're gripping the yoke, you got an idea of how much pressure to put in. But Super Decathlon, you can just grip it with a couple fingers and a thumb and very easily move the controls all around because it's designed to be a highly maneuverable aircraft. It's designed with a high amount of controllability into it as well. It's not designed with stability in mind. You don't want an aerobatic airplane to be necessarily stable because you need to be able to get it to disturb it from its datum very easily. So we say an aircraft is less maneuverable if you need large effort to move the yoke. Okay, trying a top hat question here. Right, so the amount of yoke movement needed to change the airplane's attitude. What is that known as? We've got a couple new terms here for you. Maneuverability and controllability. So movement would always mean the control surface movement, how far you got to move the yoke. The yoke's attached to the controls, right? All right, most of you got that one right, controllability. Yeah. Yoke movement, that's control surface movement, control surface controllability. Take a look at the reason why we have an empennage on this design of aircraft here. Let's take a look at a couple different terms here. Obviously, we're looking at a center of gravity position here, and that happens to be a forward position. Along this wing surface, if we were to take and just average all the lift into one point, we would have the center of lift represented by the black dashed line here. Since that center of lift is behind the center of gravity, and that center of gravity is a pivot point, that means anytime the wing's developing lift, it's trying to pitch the nose down. Therefore, we have a horizontal stabilizer here, which is effectively an upside down wing, producing lift in a downward fashion. Since pushing down on the tail, we pivot around the center of gravity point, it lifts the nose back up again. But during flight, all of the downward forces developed, the weight of the aircraft and the tail, need to be equalized by the lift generated by the main wing. So the wing has to produce enough lift for the weight of the aircraft. That's why I say if you got a 3,000-pound airplane, you need about 3,000 pounds of lift, because you actually need just a little bit more. Whatever the tail force is, that main wing also has to overcome it. So in effect, a forward center of gravity is a heavier aircraft, aerodynamically speaking. It's going to be an important distinction here when we start talking about outer limit effects here. So forward center of gravity is the same thing as a heavier aircraft. Very important to remember that one. And just taking a peek at the opposite here with an aft center of gravity, we still have the center of lift located behind it, but it's a very small distance now. So the ability of the aircraft to pivot about the center of gravity is reduced, so there's less pitch down force happening. And therefore, since the nose isn't pitching down quite as much with the aft CG, you don't need as much force on the tail now. But you still have to overcome with the main wing developing enough lift for the aircraft's weight, in addition to the load imposed by the tail. But it's a lot less of a load. If I go back to the forward CG, and you notice we have a large amount of tail down force. As with the aft CG, you have a small tail down force. So in effect, an aft center of gravity loading is a lighter aircraft, aerodynamically speaking. So again, important to remember, forward CG is heavier aircraft aerodynamically. Aft CG is a lighter aircraft aerodynamically. This will help you with out of balance effects. So one reason when we are doing the air race each summer, that we do our best to get the center of gravity as far aft during the race as we possibly can. We'll see why here when we talk about these out of limit effects. All right, so we are looking at a couple things here. Looking at takeoff and landing speeds. Let's look at this one first. Now, honestly, I only memorized one of these. Okay, I don't memorize both because the other one's just the complete opposite here. A forward center of gravity, I always remember, as a heavier airplane. And we talked about earlier, if I have a heavier airplane, I need more airspeed to get off the ground. So hence, I need a faster speed. When we look at the stall speed of the aircraft, with a heavier aircraft, right? Forward center of gravity, that's the same as a heavy airplane. I need to use either a greater angle of attack to develop the lift, to overcome it, or I need to fly the airplane faster with more engine power. Okay? Both of those have the same effect of raising my stall speed. So a forward center of gravity or a heavier aircraft will stall at a faster speed. Cruising, that forward center of gravity, which is also a heavier aircraft aerodynamically, I'm using a greater angle of attack to develop more lift. More lift, as we learned last time, is more induced drag. So I got a higher drag penalty now. So I can't fly as fast. Rate of climb. Remember we talked about the power curves last week. The greater the distance between power curves, the more excess power you have. Well, we also said if you have a heavier aircraft, then you won't be able to fly your rate of climb as fast. You don't have, you need more engine power to actually overcome the effect of the higher weight. So our rate of climb is slower. Now, aft CG, lighter aircraft, those are all the opposite of a forward center of gravity. So I don't have to memorize those. I just remember one set, the other is the opposite. Okay, top hat question. Aerodynamic perspective, forward CG, same as a heavier airplane. True or false? I'm really trying to reinforce this concept with you. All right, very good. Again, just trying to reinforce that concept with you. Right? Helps to explain a lot of these effects. With a forward CG, takeoff and landing speeds. Remember, heavier airplane. And they're faster. Wonderful. All right, try another one here. Forward CG, the stall speed, faster or slower? Heavier aircraft, going to need a greater angle of attack. Greater angle of attack means you're closer to stall's angle of attack. All right, nice job. All right, a few more out of limit effects. Looking at maximum altitude. Forward center of gravity again. Heavier aircraft. We're using a greater angle of attack to develop lift. We're using greater engine power in level flight. You don't have as much engine power to go high, so you can't go as high as you did at the lower weight. Endurance. If I'm going to operate at the same cruise speed as with the different CG positions, I need more power to do so. I'm burning more fuel per hour, so I have a reduced endurance. Range, forward center of gravity, heavy airplane. Again, I'm using a greater angle of attack. So it's more drag and a slower speed. So you can't fly as far as you did with that slower speed. Got a couple more aspects here. Stability, controllability, maneuverability with these out of limit effects. So got my crude airplane drawn up there. You can see the tail and the propeller. The white dashed lines here represent the center of gravity limits. And so you can easily see that we have a forward CG position. Okay. Forward CG. That does create a long arm and hence a greater moment force to the tail. Because you have a longer or higher moment force now, it's going to be harder to disturb that aircraft. So it is a more stable platform now. In addition, our controllability, the amount of controlled movement needed. As soon as you start moving a control, you have that big moment force here. It's going to start moving the aircraft. So you're much more controllable. However, with the maneuverability, remember that's the amount of force you have to put into moving a control surface. You have to overcome that large moment force. So the aircraft is less maneuverable now. And a very similar aspect with the aft CG, your arm is reduced, so the moment force is reduced at the tail. So flying with a aft center of gravity, that gives you less stability, because it's easy to disturb the aircraft from its trimmed condition. It also gives you less controllability. So when you start flying with passengers in the back, you're used to moving the yoke a certain amount, and that's going to be too much of a yoke movement. And you're going to start over controlling the aircraft. As far as maneuverability, you're used to putting in a certain amount of effort into the controls. Here, you don't need as much effort. So not only are you used to moving the control more, you're also used to applying more force. So you're definitely going to have a tendency to over control the aircraft in that situation. And that ends our little section here on weight and balance.